Right. We did this. We did this. We did this. We did this. Okay, so now this is the next one. Pressure at a point. So for this formula, what we'd like to know is if I have a liquid, I should draw it more like a liquid, and I have this down the bottom here, and we'll call this radius here R, and we'll call this distance here H. I want to know what is the pressure on this disc, how much pressure there is. Okay, so what is actually pushing down on this disc? What is the cause of the pressure? This is under some liquid, we'll say. So why is there pressure on this? Yeah, it's because the water above it is pushing down on it. Yeah? That's why when it's near the top, there's less pressure than if it was near the bottom. So the reason there's a pressure is because there's the water above it pushing down on it. So let's calculate this pressure. So what's the formula for pressure? I'm sure you all remember. F over A. Now what's the A in this one here? Pi r squared. Good. Now the F is caused by what? The weight of the water. Good. Okay. Good. And what's the formula for weight? mg of the water. But of course we don't know the mass of the water or the liquid or whatever it is. But we do have this formula. Density is mass over volume. So mass is density by volume. Okay, so that will be density volume G over pi r squared. Now we have a formula for the volume here. What would that be? What shape is this? It's a cylinder, yeah. So do you remember the formula for the volume of the cylinder? No, you're thinking of a sphere perhaps. Pi r squared h, yeah. Pi r squared h G over pi r squared. Now this is very interesting because what cancels here? Now because there's no h in this formula, it means if I make the h smaller, does the pressure change, the formula? Well, it feels weird because we say there's less area, so there should be less pressure. But there's also less force because there's less water. In total, the pressure is unchanged, even if I decrease the radius. In fact, I could decrease the radius all the way to 0 and just be left with a point. And the pressure at this point is equal to rho GH. In other words, the only thing that matters for calculating the pressure is the H, the value of G, and the density of the liquid. So, if the liquid is more dense, then we have more pressure. If the H is bigger, then we have more pressure. And of course, if the G was somehow bigger, we'd have more pressure. So the final result is pressure is rho GH, pressure at a point. Okay. Are we okay with this proof or not? It's easier than the first proof we did. Even if you can, I don't even know if you can remember that proof. It was like a week and a half ago. Remember? Yes, it's things bouncing around in the box.
Yeah.
You want to write this down?
That means the pressure is same whatever the radius is changing.
Yeah, it doesn't matter about the radius. So we make the radius 0. In other words, all that matters is the H. That's all.
equal density?
Density, G,
About
H.
what?
Huh?
Water?
Oh no, it can be any liquid. In fact, it can be any liquid or gas. So this formula works if it's a gas or if it's a liquid. It doesn't quite work if it's a solid because you can't really move in a solid. I mean, it actually does work. It's still true if it's a solid, but it really doesn't make sense because it's not like this point can move in the solid.
Then I put the pressure in here.
Yeah.
That density is both here or here?
Density of the water, the liquid that it's in. Yeah. This density is for whatever this material, this liquid is, or gas. Yeah.
This is only used to the circle.
No, in fact, because the ore can be zero, it can be a point. And because it can be a point, it can be many points, which means it could be anything. So, yes, anything.
In the example, they asked us to prove the
This formula, no.
other formula?
No, what I said was last time, remember the first proof we did with the box and the particles bouncing on it? That proof is too long for the exam. But it is part of the syllabus to know this proof, and they do, and they have asked students to sort of prove that they understand this proof. So what they would do in the exam is they would ask you a small question to test your understanding of the proof. So for example, they might say the formula was PV equals 3 over 2, and it was E equals 3 over 2 PV, wasn't it? So a simple question might be, what was the reason for the tree in the formula? So how did the tree appear in the formula in the proof? Does anyone remember? Yeah, because it was three dimensionals. That's why the tree was there. They might ask you, what was the cause of the P in the formula? So the P was the pressure. Well, what caused the pressure? It was the force. And what caused the force? It was the change in momentum. The change in momentum of what? Of the particle hitting the wall. So in other words, the pressure was caused by the change in momentum of the particle's collision with the wall. So they will ask you some question that tests your understanding of the proof. So you at least need to understand the proof. Yeah. What else have they asked? I think that's it. Yeah, and the other thing they like to ask as well for this proof is, what are the assumptions of an ideal gas? Do you remember the assumptions? What are they? There's no gravity, we consider. There's no force between the particles. The particles are considered just as colliding points. And was there something else? There was 4 assumptions, wasn't there?
No attraction.
Yeah, no attraction. No attraction, colliding points, no gravity. Low density, that was the other one. Low density, yeah. Okay, continue. You have this? Yep. So, we have our formula. Now, this gives us actually our next idea. So, here are the physics students. We've got them all here. I've added a few more. There now. And look, there can be me. Right. Now, we all understand that we're actually in an atmosphere. So there's actually air pushing down on us right now. And this actually, you might not realize it, but this pressure, it's kind of the same idea of what was happening here. So when you fall into water, and as you sink to the bottom, the pressure on your body increases. In fact, it's exactly the same situation here. It's almost like we were dropped into the air and we sank to the bottom, and we have a pressure because we're at the bottom of this like tank of air, if that makes sense. Let's calculate, or let's do some, not some calculations, but let's talk about this pressure here. This pressure changes slightly depending on the weather. So on a sunny day, does anyone know what happens to this pressure? Is it higher or lower? No, on a sunny day it's higher. On a day like today, the pressure is lower. Also, of course, because it depends on the H, if you're on the top of a mountain, and since the H is less, then the pressure is also less. So that's why on the top of a mountain there's less pressure. Yeah? What is the pressure? Well, in fact, because the pressure can change, it's only an average, but we say the average pressure, we call it 1 atmosphere of pressure. Now it's only an average because sometimes it's more, sometimes it's less, but we call it 1 atmosphere of pressure. And does anyone know what this value is, how much pressure that is?
101.25.
Yeah, I think 101.325. What did I use here? Just 3.5 actually. Anyways, it actually is on your calculator, if I can see. It's ATM, which is constant number. What is it? Mode 7, is it? No. Shift mode 1. Oh, come on. ATM is 40. Yeah, 101.325. I'm sorry, that's a typo I have there. I should have 325. Not here, I have 35. Anyways, I think for the exam they just care to use 101.3. 101.325 kilopascals. That's 101.325 pascals. Now that's huge. Think about that. That's 101.325 newtons per meter squared. Newtons per meter squared. So if you imagine you're on the ground and you're taken up about 1 meter by 1 meter, I know, we'll just roughly, we'll say 1 meter by 1 meter, then the force down on you is 101,325 newtons. Now, to put that more into context, yep, that's pretty big. Imagine you were on the ground and there's a giant weight on top of you. That's like a 10,000 kilogram mass sitting on top of you. That's on all of us right now, but we don't feel it. Why is that? You would think you would feel 10,000 kilograms sitting on top of you, right? What's 10,000 kilograms? That's like 5 cars, isn't it? That's how much force is on you. It's as if 5 cars are resting on top of you. Makes you sound pretty strong, doesn't it? Yes. And it's true. But why don't we feel it?
Because time keeps changing.
Huh?
No.
No? Does anyone know why?
Because we have balance.
What do you mean? Oh, there's something pushing up. True, yeah, we're pushing up with the same force. But if I ask you to lift 5 cars, you can feel that reaction, right? So why don't we feel this reaction?
Because we have the same force in
Yeah, but you should be able to feel that. Like if I ask you to lift up 5 cars, you will feel that reaction force in your body.
What's the difference? What are force and gases?
Yeah, go on, because
Those the gases
how so?
moving.
Good, not this. Yeah. Anything else?
We are used to it.
Exactly. The only reason we don't feel it is because we feel it all the time. From the moment we were born, this has been present. And because it's present all the time, we don't feel it. We're not aware of it because it's there all the time. Because it's there all the time, we don't notice it.
So if I go to a vacuum thing, I have the strength to carry 5 cars.
Yes, actually, yeah. If you were in a vacuum, like if you were, now of course you won't last so long, but if you were in a vacuum and you were lying on the ground and somebody started stacking cars on top of you, yes, you should be able to take 5 cars because it's the same force, which is crazy to think about. It's a huge force. It's a huge force, you know. Now you might think, oh, that's kind of cool. It makes me feel like I'm really super strong, which is kind of the idea behind Superman, isn't it? Like on his home planet, he's not so strong, but when he comes to Earth, he's much stronger. It's kind of the same idea if you think about it, because everything is so different for him. The pressure higher, the gravity is higher. So when we go to the moon, it feels like we can jump very far, like we're a superhero. Same idea. Yeah. So if you want to be a superhero, you just need to find a planet with G that's much less than 9.8. You'd want maybe an atmosphere, maybe 0.1 atmospheres. You know, and then it would look like you're 10 times stronger and you can jump twice as far. Yeah. So no problem, everybody can be a superhero.
Carrying oxygen tank.
It is, yeah, no, it is worth the oxygen tank for sure. Okay, can you make sure you have the right value? It's 101.325. I better fix that so I don't forget. But it's on your calculator as well. Where is it gone? Okay, did you get that? 101.325. It's on this one? It's not on this one. Should do, yeah.
Why the pressure is changing according to the weather?
Yeah, I think the reason is because the density changes. Because when it's sunny, it's hot. And when it's hot, things expand. And when the air expands, it's less dense because the volume is bigger. So if it's less dense, then that means the pressure should be less.
Yeah.
I don't know.
You know?
I don't know now, actually. Yeah, when it's sunny here, the pressure is higher. And when it's cold, like today, the pressure is lower. Good question. I don't know. You'll have to ask a weather person. I'm not sure about this one. Yeah. See, what I thought was because it's hot, it means the density is less because the air expands.
Because sunny day, because the gas goes up.
It's because it rises.
It rises. So they have more gas on the top.
Okay, so you're saying it's because when it's sunny, it's hot and the gas rises.
Yeah.
So there's more gas on the top. But shouldn't there be less on the bottom?
Yeah.
So in total, it doesn't cancel? I don't know. Good thing that this is not on the exam. So I'm not sure the reason why. It's also maybe a little bit complicated by the fact that there's water in the air, and we know that water can behave very strangely between 0 and 4 degrees. So I think I was telling you this. If you have water that's 10, 20 and 30, the water which is 30 will rise up, so will the 20 and so will the 10. So if you have a tank of water, the top could be 30, the bottom 20, the middle 20 and the bottom 10. Because, hot means expand, means less dense, means it rises. But water is very strange between 0 and 4. So this could be 4, this could be 3, this could be 2, this could be 1, and this could be 0 ice on the top. Is this our Darius friend? Oh.
Do you not recognise
No, 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 no.
I have you pestered today.
Yes, yes, you need
How do
me
you do
this
that?
time or the student?
The student.
The student this
Yeah,
time.
just a quick little announcement. Some of you might have heard about the cold weather that's on the way. Well, it already is very cold, but it's going to get colder. And there's all sorts of weather warnings being announced on the news. Now, what I'm asking you today is to keep a close eye on your phone for emails from me. Okay, don't just delete them or put them into junk mail or kind of scan through the first few lines. It could be me cancelling classes. Okay, so sometimes what happens is the government will send out a nationwide alert and saying all schools should close. Sometimes individual universities will make a decision. So, for example, if Griffith College decides to close, then we also have to close because they've decided it's not safe for students to travel. Okay, there's a couple of different reasons. Don't just go by what's on the news. Wait for an email from me.
Yeah, because sometimes it could just be the schools for the little kids that would close, but not say high school or university. So, I know. Yeah. Look, you're thinking you really want a snow day. I assure you, the teachers are thinking it more than you are.
Well, actually, do you know something? From my perspective,
Yes.
I really don't like a snow day.
Because
Yes. Yeah.
Because then I have to fit in all the classes somewhere else. You know?
Yeah, but that's a
But that's
principal
the thing.
problem. That's not a problem for the students or the teachers to worry
Indeed,
about.
indeed,
Yes.
indeed. But the other thing is, even if classes aren't cancelled tomorrow, it is going to be very cold. It's probably going to be, it's actually started snowing already. Have you seen that? Yeah. So that means that it's going to be dangerous if you're travelling. So just take care, wear sensible shoes, not like mine. Make sure that you don't take any stupid risks crossing roads because traffic will be, dangerous. So just be careful and keep an eye out for email alerts.
Are you here to tell them to mind themselves crossing the road and to
Pretty-
bundle up warm and make sure they wear a sweater?
Well, see, some people come from places where you would get extreme cold weather, but if you've never been in it before.
I saw a business student in September earlier today walking around in shorts.
What? Okay. See, we do have to
Yeah.
say these things.
Yeah.
Dress warmly.
No
Don't
shorts.
be an idiot.
No shorts.
No shorts.
You might know this student as well. You can have a think about it.
Oh, cool.
Yeah.
Okay. Anyway, sorry for disturbing.
No problem, no problem.
Yet another one of your classes today.
No, we'll all bundle up warm, won't we? Yeah, we'll wear sweaters and everything, yeah, okay. Okie dokie.
Yes.
So actually, with that saying, between 0 and 4, the water behaviour is actually a little bit strange. The 4 actually sinks to the bottom. I don't know if this is affecting the pressure for the weather as well. Okay. So we have that. Oh, and the other thing is that pressure is at sea level. Of course, if we go up to a mountain, it's less, and if we go down to a valley, it's more. Oops. Right. So, here's a small question. Guys, if you can try this one. What is the pressure on you if you're swimming 5 meters below sea level? So this is the pressure if you're 5 meters under water. In the sea. Well, oh, I see. Should we use, very good, should we use salt water?
Yeah.
I actually wasn't thinking that because I never said you were swimming in the sea. I just said 5 meters below sea level. Yeah, let's say it's let's say it's seawater, salt water.
what is that?
Yeah, I don't know. 1030, I think, is it?
There it is. Okay.
1030 or 1020? 30.
How do you get the atmosphere? Like, what do you put before or after?
What do you mean?
Like, you just put the atmosphere.
Oh, on my calculator, it was constant number 40. That does not have it, and that does not have it, that does
No,
not
but I
have it.
have the ATM.
Oh, do you?
Yeah.
What is
But, like, I should do something before or after.
The number one, just, I think.
I tried.
And what's it saying?
Syntax error.
Syntax error.
What is G?
G is 9.81.
Underwater, is it?
Ah, yeah. How do I go back? Oh, something. No, I think this one. How do I delete the one? How did you get the ATM up? Let me see what the menu was. There's just something. How do you normally call constant? You know, like, have you used constants on this calculator before? What are they doing?
Where did you go?
Yeah, it's strange. It shouldn't be so difficult just to get the value up. What if I do this? I'm out of ideas. No, we've already tried one and it equals, yeah. Anyways, you got an answer here?
Yeah.
What you got?
50521.5.
Yeah.
What's it in kilopascals? 50 kilopascals? 51 kilopascals. Okay. Got that?
Yeah.
Do we use density or relative density during calculation?
Oh, we always use density. The only use of relative density is just when you're given a density. Like I might say the relative density of this is 0.5, but you would never use it in a calculation for our class. Right. Here's an interesting one. How thick is the Earth's atmosphere?
There are
Yeah, how thick is the atmosphere we're in?
I think the
7.
Well, the atmosphere, there's kind of, in my mind, there's kind of like two parts of the atmosphere. It's the part we care about, the air, which is, you know, the oxygen part, and the nitrogen. Is it nitrogen N2 or just N? I think it's N2, isn't it? There's this part here, and also there's a huge outer layer, which, you know, very, very low density and so on. It's actually this one that I care about. We kind of, let's pretend that doesn't exist. It's the one that makes the pressure. So we could actually calculate the thickness of the atmosphere like this, because we have pressure equals rho GH. Now let's do some very rough calculations, okay, very rough calculations. So roughly what's the density of air? Does anyone remember? It's 1 point something, isn't it? So we'll just say roughly 1, okay, roughly 1. So, what's wrong? Question? No? So we're saying the density of air is roughly 1. And the pressure is roughly 1 atmosphere. So let's just do these calculations roughly. Well, 1 atmosphere was 101 kilopascals. So let's just make it easy and say it's 100 kilopascals, just to make it easy.
100.
The density is roughly 1. What's the G? Oh, sorry, that's 100 kilos. So let me put in 3 more zeros. 1 and 10, and the H is what we want. So we can see very, very quickly that the H must be roughly 10,000 meters, or in other words, the H is roughly 10 kilometers. Now, of course, this is only an estimate. There is a small problem with this formula. This formula assumes the density is constant, right? But we kind of know that the density is not constant, because as you move up, what happens to the air? It's less dense, isn't it? So the density actually is decreasing. So it's not quite right to say that it's 1. It's not quite right. because here the density is 1, but up the top the density would be 0. So if it's not quite right to say it's 1 for this problem, what would be a better value to say?
Average.
The average, which would be about
0.5.
0.5. So if this was instead a half, then what would change in this answer? It'd be double, wouldn't it? So my guess is that the atmosphere that we breathe in is about 20 kilometers. It's a rough estimate. In other words, 10 to 20 kilometers. This is what I think roughly. Now you might say, well, that's kind of a big error. But remember, I was doing all these calculations in my head. It's not like I was doing any kind of special experiment. So I think this is actually pretty good for just something we're imagining. You know, and if we really wanted to, we could calculate it exactly. So I'm going to say somewhere between 10 and 20. I think 10 is too small, because remember, 10 is 10,000 meters, and Mount Everest is 10 kilometers, right? And people have been on the top of Mount Everest. So it's not like there's no air, it's just that there's not much air. So 10 is definitely too small. So I'm going to say 15 to 20 is my estimate as my final answer. So why don't you Google and see what we get, see how close we are. So how thick is the Earth's atmosphere? Now remember, the atmosphere has many different layers. I just care about the bottom layer, the layer that we live in. Anybody get a Google answer yet? Any answers? Yeah, from looking at the picture, the ozone layer, which is kind of a little bit about kind of the limit. The ozone layer begins at 20 and ends at 30. So the ozone is from, you know, ozone layer being the top. The ozone layer is from 20 kilometers to 30 kilometers. So this is kind of the top of the atmosphere that I care about. The atmosphere after that is so small it's not important. So my answer wasn't too bad. I said 15 to 20, and the answer is more like 20 to 30. So, you know, it's not 20 to 30. So my answer of 20 at the beginning was actually pretty close. A little bit too small. Yeah. Okay. The reason I wanted to do this question was to show you that with a little bit of physics and a little bit of knowledge, you can actually really get interesting questions answered like this. You know, I can't do this in biology. Right? Just can't. Okay. So you don't need to write this one down. This is more just a thinking about question. Now, how many questions did I give you on the worksheet for this one? Six, was it? Was it? It seems a bit... I made a mistake. I called the same page the same name twice. There's two lessons called Simple Kinetic Model of Gases, is there? Yeah. See, the same name here and here. They have the up-to-date one? No, not ideal. Yeah, this one here. You're looking at the one with the picture of the rocket on it. Yeah. Yeah, okay. Let's see, what time are we at? Yeah, can you just take 5 minutes to try a couple of these and then we'll go on to the next lesson? Which question do I like the most? I like them all. I like number 2 because it's about reading. Okay, you can try these for 5 minutes. Can I close this?